All right, what's up, everybody? So, this is the last video before we get into our Christmas break, and I'm so excited. Hopefully, you guys have some really exciting plans for Christmas. Me and my family do, and I love this time of year. Merry Christmas to all of you all, and hopefully, whenever this Christmas break is over, we get to be back in person and get to have you guys in the room because I miss you guys dearly and this year just has not been the same without having you guys here. But want to tell y'all Merry Christmas. Let's finish up this chapter 3, section 3. Finish this off talking about general overview of chemistry stuff. And this one's going to be on the states of matter. I'm not going to spend a whole lot of time on it because I think you guys pretty much have a feel for this. I'm pretty sure you've heard of these before, and it's some class that you've taken. So let's just get rolling right along with it and talking about the first state of matter that you guys have definitely heard about, a solid. So it's like what you're thinking. We're going to talk solid, liquids, gases. I was going to talk a little bit about plasma for the fourth state of matter. But in this, we're going to focus on solids first. So these are just substances that are densely packed particles of ions, atoms, or molecules. This is the thing, they're tightly compact. These things are really in there, really close together. And in this, most of the solids are in a crystalline structure. And in that, like talking right, where's the mouse? There it is. These crystalline structures, because those particles of a solid are arranged in this rectangular geometric pattern, and it's split out that way to build strength, stability to the solid, and it's giving solids definite shape and volume. So you see this a lot with ionic bonds. Um, it's what they really like to do. Another example is of glass, and that's just a solid that consists of densely packed atoms arranged randomly. So that's where we're going to talk about solids, and that's pretty much it. So let's talk about liquids. You guys know the liquids. We drink liquids all the time. Uh, like perfect example for all states of matter, the three big ones is water. So the first one is like ice, like in your iced tea or your iced coffee that you're drinking right now as you're watching this video, or as the iced coffee I wish I had right now, just getting to drink it, but I'll drink my water. This is liquid water, okay? And with it is we'll see increase in temperature increases the thermal vibrations of atoms in a solid. I know that can be a little confusing, so to kind of explain it to you, pretty much you increase the temperature, everything's moving. Okay, everything's always moving. The particles uh, and atoms inside of things, they're moving. Also, if you've ever watched The Flash, and it talks about the vibrational, the frequency of things. That's like what he's talking about is how they vibrate. Everything vibrates and shakes at a certain phase whenever he's phasing. And with this, it's the same thing. If we increase the temperature, then what will happen is we increase the temperature, it's going to vibrate a lot more. And those things are going to bounce around a lot more. It gives more energy into it so it can take solid things and make it into a liquid. Like an example is if you go out with a pot and you put a bunch of snow in it, and then you stick it on the stove, what happens? The snow will melt to a liquid, to a water. All right. So when these thermal vibrations become vigorous enough to break the forces holding the solid together, the particles can slide past each other and the substance becomes a liquid. And these take the shape of the containers that they are placed in, but they do have a definite volume. Okay, so it has a certain volume with it, but it'll take the shape of the container. So, like my bottle of water here, this water that's in here, it can take the shape of my water bottle, or it can take the shape of this beaker. If I poured it in this, take the shape of a coffee cup. It takes the shape of whatever you put within it, even though it has a definite finite volume. Okay, and that's what we do a lot with liquids, especially if you take chemistry and all this COVID junk has gone. By the time you are, that's 2 years from now. It should be gone by now. By then, I pray, and we'll actually get to do labs. in chemistry, and that's something you'll actually get to learn. One of the first labs we do is checking precision and accuracy of different instruments we use within the lab, and it works on your technique of them. So then we have gases. So sticking with putting the snow on the stove, it melts to liquid, but then there comes a point where not only do you have that liquid, if you leave it on the stove anymore, then we increase the temperature or increase the thermal energy. There's more energy in there, so now those molecules or particles or atoms, they're vibrating even more violently now. And so what happens is they expand out more with more energy, and it goes from a liquid into a gas. So this is steam, okay, for water. This is when we see the steam coming off. If you want to see something really cool, wait until it gets really, really cold again and go outside with a pot or a cup of hot water. Go outside and throw it away from you. Now, throw it away from you. Don't throw it over you or around you or towards anybody because this is hot water. It will burn you. But if you throw it out, you'll see like when you got a liquid and it rushes out where it's so cold, it just automatically in the steam. It's one of the coolest things. Just be extremely, extremely careful when you're doing it. Make sure you have parent supervision and your parent gives you permission to do it. That way we're covered and don't have any issues there. So this process of change from a liquid to a gas at temperatures below the boiling point, called evaporation. Hopefully you guys have heard this through the water cycle before, precipitation, evaporation, condensation. Hopefully you've heard of these before. So gases, like liquids, have no definite shape, but they have no definite volume unless they're restrained by a container or a force such as gravity. The gravity is what holds all like the atmosphere, like the gas in our atmosphere here on Earth. But another example is whenever we put helium within a balloon, why does the helium not just blow out? Is because that balloon is there and it constricts it in and won't allow it out. It can't move out from it, so it takes the shape of the balloon. And this last one, this is one that I've always been interested in, and you guys have probably heard it a bunch of times. So this one's on plasma, and all plasma is at extreme temperatures will have collision between particles in matter that are so violent that the electrons are literally knocked away from those atoms, resulting in a hot, highly ionized electrical conducting gas called a plasma. That's all it is. I don't expect you really to like go much in depth with this. Even in college, we never really discussed this, so I just want you to know what it is, just to get it out there. But then we have different changes of state of matter, and this one's big for us. So solids melt when they absorb enough thermal energy to cause their orderly internal crystalline arrangement to break down. This happens at the melting point. So the melting point, that's when we have a solid goes to a liquid. So like an ice cube goes to liquid water. Then when liquids are cooled, they solidify at the same temperature and they will release thermal energy. The temperature at which liquid solidifies is called the freezing point. Okay. Right now, everybody out there normally would be so caught up on this because of what? We care about snow. It's like, oh, we're gonna get a snow day. Oh, we're gonna get a 3 hour delay. Oh, we're gonna get a snow day. Yeah. In this, that's what we're looking at is the freezing point. Is it hit that freezing point? And then we worry about below the freezing point because we're like, man, if it's like 33 or 32 degrees, it's going to snow, but it's not really going to stick. And you're like, oh, I'm not going to get my snow day. Uh, so when a liquid is heated to the boiling point and absorbs enough thermal energy, vaporization occurs and the liquid becomes a gas. So vaporization is like a vapor, is whenever the thermal energy gets so high, the liquid turns to a gas. That's our boiling point. So when we have a gas cooled to the point, uh, the boiling point, it releases the thermal energy and comes back to a liquid. That's condensation. The slow change of state from a solid to a gas without an intermittent, excuse me, liquid state is sublimation. Sublimation, the only real example I got for that is carbon dioxide. We'll use it, it's called dry ice. People will get that to put in coolers so it won't give them water, but it'll keep everything cold. So that's kind of like, I don't know if you guys have ever seen dry ice before or not, but that's kind of like what I get with give you for sublimation. And then the conservation of energy. This is a hugely, very, very important aspect is to know this because the fundamental fact matter cannot be created nor destroyed. That's the conservation of matter. Like matter, energy cannot be created nor destroyed. It can only be changed into one form or another. We do this all the time, literally in vehicles is a perfect example. You take the energy that is stored within molecules of gasoline, it ignites, and it's transferred into motional energy that we use to push our cars down the road, but it also comes off as in heat. And this is the thing that we get. You never can, it's so hard to get 100% energy out of something. It's extremely, extremely hard to get that constant, that much energy from something. You want to try and do that. We keep trying to make everything better, that we'll keep getting the energy into the form that we want it. But cars are a perfect example because not all of that energy goes into us driving down the road. Some of that energy is released in heat. We'll convert it into heat, which causes that's literally for us, it's just wasted energy until like right now in the winter, and then we need the heat to keep us warm in our cars as we drive. But we're losing a bunch of energy. Now, this law is the conservation of energy, also known as the first law of thermodynamics. All right, ladies and gentlemen, that is it. We have officially finished chapter 3. Hopefully, I see you back here in person in this room. And I wish you and your family the greatest Christmas. I pray you guys have a wonderful Christmas. If y'all need anything, please reach out to me. Besides that, have a wonderful day.